Imagine a world where scientific discovery never stops. No lunch breaks, no sleep, just an endless cycle of curiosity. New ideas being born, tested, refined, and published every single day by AI. Now, this isn't science fiction anymore. So, hello guys, welcome to the new video in which we will be reading a research paper that has introduced something called the AI scientist, an artificial intelligence that can actually do scientific research from start to finish. It thinks of new ideas, write code, run experiments, creates visuals, and even writes and review its own scientific paper. Yeah, you heard that right. It can literally write paper good enough to pass in submission to a top-tier machine learning conference. Yes, this first line sets the stage. The author are talking about one of the ultimate goal of AI, creating an artificial generated intelligence or AGI. That means a machine that can think, learn and reason like a human across any domain. And here they are saying one of the hardest part of reaching that is building an AI that can actually do science, not just repeat facts but discover new knowledge. So, to really understand the AI scientist, we first need to talk about how science itself works and how it's been done for centuries. Think back to 1600s and 1700s, the Enlightenment era. This was when humanity formalized the scientific method, a process that still drives even discovery today. A human researcher gathers what's already known, forms a hypothesis, designs experiments, collects data, and draws conclusions. Then they write a paper, send it for peer review, get feedback, and refine their work. This process repeated millions of times. This is what gave us everything from vaccines and semiconductors to internet, but there's a catch. Humans have limits. We can only think of so many ideas, test so many hypotheses, and read so many papers. So the question is, can we make AI systems that also do science, not just analyze data and create new knowledge? This idea isn't new. People have dreamed about automated science since the 90s, 70s. In fact, early systems like Dendral and the automated mathematicians were among the first attempts. Dendral helped chemists identify molecular structure using computers, and the automated mathematician tried to discover mathematical theorems automatically. These were ancestors of today's AI-driven research tools. Then, as artificial intelligence evolved, researchers began to imagine something even more ambitious, AI that could improve AI itself. Recursion? Yeah. So this idea sometimes called recursive. Oh wow, this is in line. This idea sometimes called recursive self-improvement means building an AI that invents better AI, a kind of feedback loop of innovation. It's like training a model that's not only learns tasks but also learns how to design the next generation of model. But in recent years, things have started to get real. Massive foundation models like OpenAI, GPT, Anthropic, Claude, Google DeepMind, Gemini, Meta, Llama, they have become generalist. Like, these models are smart enough to help in the research process. They can summarize paper, brainstorm ideas, write code, generate figures. But here's the key limitations. They still only handle piece of the process. They don't yet perform end-to-end scientific discovery without human guidance. In older automation systems, humans have to predefine the search space, the boundaries of what the AI could explore. Think of giving an AI a fenced playground and saying you can look for discoveries only inside here. It's like this. You can only look discoveries only inside a certain boundaries. That works great when we know the rules, like in material science or biology, where you can tweak known molecules or proteins, but it's not real open-ended discovery. It's a targeted process, not a creativity. And this is where the AI scientists come in. This system doesn't just help, it takes over the entire research pipeline. You give it a broad research direction and maybe some initial code, and it does the rest. Wow, no, nothing, just a lazy one like me. So let's unpack that, what it is. Ideation, literative search, experiment, manuscript writing, peer review. And then it loops back, improving itself in next research ideas using what is learned from the previous ones. That's what they mean by the open-ended loop. And the whole thing runs at a cost of about $15 per paper. Just $15 per paper. It took many. That's mind-blowing because it means you could theoretically run hundreds of research projects for a price of one research paper, like one human researchers. Even the coffee budget is more of a researcher in writing a research paper. So the AI scientist uses two powerful mental models borrowed from cognitive science and AI research. First is chain of thought reasoning, where it breaks down problems step by step logically, like it's showing its work. And another is self-reflection, where it looks at its past mistakes or results and adjusts its next plan. Together, this gives a system a kind of metacognition, the ability to think about its own thinking. Ability to think about its own thinking. For example, imagine you tell it, explore how transformer tensions affect learning speed. Answers. So it will go like search for relevant research, modify existing code, run experiments, plot graphs of the result, then draft a full paper explaining what is discovered. It even reviews its own paper using criteria from real conferences like clarity, originality, and significance. Then it stores all of this in a archive. So future AI projects can build on previous discoveries. That's how it mirrors how human science grows collectively. That's what we humans do. So now comes the background. This explains the core technologies that makes the AI scientists possible, and it starts with large language models. These are the same kinds of models behind every systems like ChatGPT and all things what we are using right now. Technically, they are called autoregressive models, meaning they can predict the next word or token based on the previous words that came before. This is the reason why Claude and all these models are weak in maths, because they just predict the next token. So, as mathematically written as px1 xt minus 1 theta, you can think of it like a super advanced autocomplete. It doesn't just guess the next word but builds entire paragraph that makes sense, answer questions, reason logically, and even write code. Because they are trained on massive amount of data and huge neural networks, these models develop what seem like human-like abilities such as common sense, reasoning, logical thinking, and problem solving. But LLMs alone are like brilliant thinkers without structure. So researchers embedded them into agent framework. This means wrapping the model in a system that guides how it thinks, acts, and improves. For example, when you see a model that shows its reasoning step by step, like Gemini, that's called chain of thought reasoning. Or when it checks and refines its own answer, that's self-reflection. These frameworks gives the model a more stable, reliable personality, like giving a scientist not just intelligence, but also discipline and method. So, finally, the author mentions about Ada and the LLM powered coding assignment that allows the AI scientist to actually write and edit computer programs automatically. Think of Ada as the like AI pair of hands, like ChatGPT with hands. When the AI scientist has an idea like testing a new algorithm, Ada writes or modifies the codes for it. Ada is evaluated on a benchmark called SWE bench, which tests how well coding assignment fix real GitHub issues and archives an impressive 18.9 success rate, which modern models. Combined with the AI scientist reasoning framework, these reliability makes it possible for the system to fully automate the machine learning research processes, from idea to working code to results. The AI scientist runs like a full research lab in three phases, as you can see in the like this: idea generation, experiment iterations, paper write-up, and plus 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 LLM reviewer at the end. Practically, you give a tiny starter code template, for example, a small Shakespeare training script that finishes in a minute, and a LaTeX skeleton with simple plotting. From there, it's free to explore any directions while keeping run small for compute efficiency. Think fast proof of concept. So, in idea generation, the system brainstorms many candidates inspired by evolutionary, open ended research. It grows an archives of ideas, uses the LLMs as a mutation operator, and attaches self scores like investigations, novelty, feasibility, etc. etc. It then refines the ideas with chain of thought and self reflections, and then filters near duplicates by querying semantic scholar to keep only truly novel ones, like a researcher checking literature before commenting to an experiment. And then in experiment iteration, the coding assistant's Ada plays a run list, edits codes, and executes. On errors, timeouts, it automatically fixes and retries. Like it's given it up to 4 times it updates. So we need to keep a threshold. Keeping the general style notes. Replans based on results, repeats up to 5 experiments before generating. Imagine tweaking a learning rate schedules, rerunning and logging curves without a human touching the keyboard. So in paper write-up, Ada fills a later conference template, section by section using only real results and figure. Then performance web search for reference up to 20 rounds. Adds adds bib text automatically, runs a final self-reflection pass to deduplicate text, and complies with a linter that feeds Ada back for autofix. So you will end up with a clean camera-ready manuscript. Finally, an LLM-based reviewer scored the paper using a standard conference criteria, and the feedbacks plus artifacts go back to archive, closing the loop for the next iteration. Now comes the big part of the real science. Imagine LS peer review. That is the peer review. Experts read paper, score it for quality, and decide if it should be accepted or not. That's where the main conspiracy come, like we spend thousands and thousands to and it gets rejected. So the AI scientist copies this system with LLM reviewer, like a version of GPT-4o that reviews paper not just like your IPS conference reviewer. It reads the raw PDF text passed with PYMU PDF and output structure results, numerical scores for soundness, presentation, contribution, overall quality, and confidence, plus list of strengths and weaknesses, and a small, simple accept or reject decisions. These scores can later be post-calibrated by setting a threshold. Example, it accepts if the score is greater than 6 or 7. In test, on 500 ICLR 2022 paper, the automated reviewer reaches 70% accuracy with combining several agent techniques like self-reflection, few short examples, showing it how real reviews look, and answering ensembling or like its average over multiple runs. Human in similar studies reach 73%. So the gap between 70 and 73 is still small and impressive. The AI got higher F1 score of 0.57 and a human is of 0.49 and equal AUC 0.65, meaning it distinguishes good from papers about as well people do. It also makes fewer false negatives, that's 0.39 versus 0.52. So it less likely to reject truly good work. So to check consistency, the authors compared how closely two human reviewers agree. Correlation is equal to 0.14 versus how closely the AI scores matches the human average. That's 0.18. So the AI actually more consistent with the community consensus. Each review cost only between 0.25 to $0.50. Few, making large-scale reviewing cheap. So they also tried other models, Claude Sonnet 3.5, GPT-4o Mini, and Llama 3.1 4405 Bay, but those were either over-optimistic or failed to follow the review format, showing GPT-4o is still the best. Overall, this section shows that an automated GPT-based reviewer can already reach human-level reviewing quality at a fraction of a cost. So let's take an example. Think of it like an AI conference reviewer paper that reads 500 of papers overnight, gives scores and feedbacks, and matches human accuracy but costs less than one coffee per review. Wow, this is a bit hectic also, like it's taking the jobs of AI reviewers. So let's take this table for a review. Each row is a different reviewer, like a human random or an AI model, and each column measures how good the reviews are. Here what these matrices are mean. So balanced accuracy is the overall correctness. Accuracy is simple percentage to of correct acceptance or reject decisions. F1 scores is all you know what it is. It's how well the reviewers balances catching good papers and avoiding false alarms. Now AUC is the area under curve. How well it separates good versus bad paper. FPR is false positive rates. That's how often it wrongly accepts and a bad paper. It comes in F1 score. And FNR is false negative rate. How often it wrongly rejects a good paper. That's what it is. Now, the human neuro IPS. It's a row. In this, it's a real world baseline. That's 0.73 accuracy, as I told earlier. It gives a random guessing gives it 0.50. And below is the AI reviewers. That's GPT-4. GPT-4 one shot and 0 shot. Then Sonnet 3.5. And at the rate 6 means they set a threshold score of 6. That's weak accept to decide accept or rejects. That's the calibrated version. Now this figure shows how well the AI scientist automated reviewer using GPT-4o matches real human reviewers from ICLR 2022 conference and how different improvements make it smarter. So the 4 heat maps at the top are confusion matrices. They compare what the AI reviewer decided versus what human reviewers actually decided. The darker diagonal boxes means the AI agreed with human more often starting from the left to the right. The base GPT-4o model reaches about 66% accuracy, adding reflection raises accuracy to 68% using ensemble reviews. So now it keeps an accuracy but gives teeter results and combining both with one-shot prompting. Showing one example of how a review should look pushes accuracy to 70%, almost matching the human reviewers. Now, below are the three scatter plots measures how similar the AI scores are to humans. The first plot, that's reviewer A versus reviewer B, shows how human reviewers their correlation is about 0.14, meaning humans often disagree. The middle plots, that's open review versus LLM, shows the AI versus the average human reviewer. The correlation is 0.18, so the AI is actually more consistent with the community consensus than individual humans are with each other. So, the last bar chart on the right summarizes the accuracy improvement across model settings, GPT-4o, and reflection, plus one-shot prompting performance based. So what you have understand is, like, I will summarize it it's an example. Think of it like a grading 500 student essay. Two human teachers might agree only 14% of the time on scores, but the AI reviewer agrees 80% with the class average. So it's slightly more reliable, and when you let it double check its work and show it how one good sample review, it actually accuracy jumps from close to human level. That's what it all means of graphs and tables and all things. Now, this section presents a case study showing how the AI scientist works in practice using real examples. The system was asked to research diffusion modeling, a popular method for generating images, and it reproduced a paper titled Adapted Dual Scale Denoising. The idea came during the sixth iteration of the algorithm, proving that AI improves through repeated cycles. Its goal was to enhance how diffusion models capture both global structure and the local details, the fine stroke textures, by designing a denoising networks with two branches, one for each scale. This approach reflects what human researchers do when improving generative modeling like VAE or GANs, but here is what proposed autonomous by the AI. Impressive, na? So this system created a full experiment plan, code editors, baseline, matrices, and plots, showing strong reasoning skills. However, as seems in many LLMs, it sometimes overestimates how novel or feasible its ideas are, a form of bias. Still, the final novel tag shows that after checking semantic scholars, the AI scientists believe the AI was unique and existing literature. It's unique in like what has built right now currently. Now, what the idea is? The idea is adaptive dual scale denoising. It proposes like it's what the idea is, what it's give, and it's what the idea totally is. The interestingness is 9, feasibility is 8, novelty is 8, and the marked is at novel because as first we have threshold of 3, so it means it found no existing paper with the same approach. It's what the idea is. Now, this section shows how the AI scientist actually changes and improves real code during its experiments. It generates a code difference, like red is detected lines, green is new lines, showing meaningful algorithm updates. In this example, it modified the MLP denoiser network by adding two separate processing paths, a global network for overall structure and a local network for fine details, and introduces a adapted weighting network with a leaky ReLU activation to dynamically balance their outputs. Now, the leaky ReLU helps avoid dead neurons by allowing small gradients for negative values, and the final softmax layer ensures that the learned weights stay between 0 and 9, so keeping the output stable impressively. Like the AI scientist iterates on its own results, it experiments, fails, and produces unexpected visuals. It revises the code automatically, just like human researchers, tweaking parameters like hyperparameter tuning or grid TV or random search to improve a model's performance or visual quality. Now, imagine an AI trying to make sharper yet smoother generated images. It adds one branch to capture global spaces like face outlines and another for details like hair strands that adjust how much each branch contributes based on the training step. Now, this describes how the AI scientist automatically writes a complete professional quality research paper after running the experiments. It produced a 11-page manuscript just like one you would submit to a real MLM conference with clear math, visuals, results, and even future work ideas. The paper explained the algorithm precisely using LaTeX math, listed all the dataset baselines, hyperparameters, and reported consistent results. Even I can't do this. I haven't wrote any research paper yet. It even rounded long decimals to 3 digits correctly, like 12.8% reduction in KL on the dinosaur datasets. It also created new plots showing how adaptive weights evolved during denoising and suggested scaling to higher dimensions as future works. However, it made small mistakes like misreporting GPU type, over positive phrasing, 3.3 improvement for wrong results, and listing every intermediate runs, which human wouldn't do. The automated reviewer later noted these issues, such as small limited dataset scope and extra compute costs, but praised the AI for being transparent and its weaknesses. It shows like it behaves like a real self-critical scientist. Now, what are my final comments on this section is the author evaluate the AI scientist generation paper using their own expertise in diffusion model. Like currently till now, what I feel is like, what if they create an experiment and all these things? And this paper is also written by AI. Okay, back to the topic. Now, they conclude that the AI chose a valid and creative research direction, similar to like work on modify attention mechanism and executed it well, even improving its code literally. Like it's iteratively after weak results, just like a real researchers refining experiments. However, they note that while the results were good, the paper's explanation for why it mentions works might be oversimplified. The supposed global versus local split code actually behaves like a mixture of experiments model, a structure often uses in large language models where it separates different branches specialized on different tasks. This shows that AI scientists can produce working innovations it doesn't fully understand yet. So the authors also highlight that identifying such subtle issues still requires human domain knowledge. But as AI is growing stronger, humans might face the challenges of super alignment, keeping up the AI generated insights that are difficult for people to interpret. Overall, they rate the AI scientist at a level of every career ML researcher, capable of designing, coding, testing ideas, but needing supervision for deep theoretical reasonings. Imagine a grad student who runs clever experiments and gets stronger results but can't fully explain why they work. That's roughly how the AI scientist behaves right now. Like, I got a one more examples. Like, you write in your major project, you write the whole summary paper, project, make project, and when the teacher asks you what this line do or what the code is about, and you are blank, you don't know why it worked out, or if this comes the error, you are unable to solve this. That's what it is. What I feel it is. So in this section, the author evaluate the AI scientist performance across different large language models and research templates to see how well each one can autonomously generate scientific papers. They tested four models: Claude Sonnet 3.5, GPT-4o, DeepSeek Coder, and Llama 3.1 405B model. Using simple starting ideas like changing learning rate or batch sizes, what we do hyperparameter tuning, then letting the system generate around 50 new research ideas per run. Each run took about 12 hours on 8 NVIDIA H100 GPUs, producing several full papers that were automatically checked for novelty and quality using the LLM reviewer. Interestingly, Claude Sonnet 3.5 consistently made the best, most complete papers, with GPT-4o close behind but struggling with LaTeX formatting errors. The open weight models like DeepSeek Coder and Lemma 3.14b model were cheaper but less reliable. So there comes the cost and accuracy trade-off. It often missing sections of misusing coding tools, but each paper ended up costing only $10 to $15, showing how scalable and affordable the automated research could become. For example, imagine giving four students the same assignment. Claude writes the most polished report, GPT-4 writes good one, but forgets some like maths formatting and all things, while the other two hand in incomplete drafts. This experiment proves the AI scientists can run across different AI models with varying efficiency and quality. Now let's check this table, which shows 10 research papers that were fully generated by the AI scientists across three different experimental themes. One is 2D diffusion, NanoGPT, and grokking. Along with the scores each paper received from the automated LLM reviewer, the reviewer scoring follows the Neuro IPS conference guidelines, where a score of 6 or above typically corresponds to an accepted paper. Most of the AI generated score was between 3 to 5, meaning they are close to, but not yet, at top tier acceptance level. Still impressive considering they were written without human input. So now, for example, under 2D diffusions, titles like dual diffusions adapted feature balancing for low-dimensional learning models, generative models, and multi-scale grid noise adaptations scored 5 and 4, showing that AI scientists produce well-structured, relevant research ideas in generative modeling. Meanwhile, in grokking-related studies, which explore how neural networks suddenly generalize, the paper Unlocking Grokking, a comparative study of weight initialization stat-D scores 6, matching human-level quality. In simple terms, this table highlights that the AI scientist can independently generate diverse, high-quality research papers across multiple ML topics, with some teachings or with thresholds of human acceptance first. Now, this section focuses on how The AI scientists explored diffusion modeling, a method used in generative AI to create data, like images, by gradually removing noises. Here, the system works on low-dimensional dataset, simpler 2D shapes like moons or dinosaurs using a modified version of the tiny diffusion codebases. Each generated paper presents a unique algorithm improvements to diffusion model. For examples, in dual scale diffusion, the AI added two denoising branches, one for global structure and one for local details, combined with the learnable weighting functions over time, showing strong quantitative trains. Another paper was model scale grid noise adaptations. It dynamically scaled noise using two grids, that's 5 cross 5 and 20 cross 20, to enhance the generation quality depending on how spatial positions, what are these and all things. Now there come the third one, that's GAN enhanced diffusions. It introduces a discriminator like GANs to guide the diffusion process, reducing the unrealistic samples. Finally, the dual diff extended the ideas to a mixture of experts, like using a diversity laws to make each experiment specialize in different data regions. Like together, all these results show that the AI scientists can independently develop, test, and visualize advanced ideas comparable to real ML research progress. Now, let's take an example. Imagine teaching a robot artist to paint not just with one brush, but two, one for broad strokes and other for fine details. That's essentially that what dual scale diffusion did. It improves image generation. That's how it improves like global and local what we get. Now let's look at this figure. The violin plots visualize the distribution of reviewer across y-axis for paper produced by each LLM. These scores follow the neuro IPS style ratings ranging from 2, that's for strong reject, and 6 to weak accept. You can think of each violin as showing how spreads out the concentrated the scores are. The wider means more varied results. You can see Claude Sonnet 3.5, that's in the blue one, consistently achieves the higher and most stable scores, clustering near 5 to 6, meaning many of the papers would be close to near IPS level acceptance. 4.0, GPT 4.0 is in orange, that performs well but with slightly lower averages and more variability. Some papers were strong, others were weaker in all things. DeepSeek was in green and Llama was in red. These scores are much lower, often near like 2 to 3 scores. These are weaker papers quality and less consistency. Now, this table summarizes the quantitative evolution of paper generation specialty for the diffusion model experiment. From this, we see Sonnet 3.5 is the best overall. GPT-4 performs comparable but struggles with LaTeX and formatting finishing. DeepSeek Coder is cheapest but the paper quality is the lower. And the Llama produced the weakest results but was the most convenient for repeated runs because it is cheaper. Now, in essence, Claude 3.5 is the most compatible researchers. GPT-4 is the comprehend but inconsistent student. DeepSeek is budget. DeepSeek and Llama is budget options with mixed results. Now, the AI scientist applies its framework to language modeling, specifically using transformer-based models for next token production. The core task behind systems like GPT, because this area is already highly optimized, finding new breakthrough is difficult, and some AI generated ideas can appear promising but are technically flawed. For example, accidentally using information from the future tokens, which artificially lowers perplexity. That's a metric. It's not that perplexity of Urban 7 hours. It's a common matrices for text predictions. Using a modified nano GPT setup, the system trained smaller transformations or character level datasets like Shakespeare, NVIC 8, text 8, tracking losses, and visualizing the training curves. Among the generated papers like Style Fusion, introduced a style adapter that changes the model's behavior per token, allowing it to mimic multiple writing styles, but possibly just by increasing model size rather than introducing a new true novelty. Yeah, that's not a true novelty, that's just increasing the model size. Now, the another paper that's adapted learning rates in transformers via Q-learning. That is creatively used reinforcement learning for tweaking learning rates during training. Although conceptually flawed because the training process isn't stable environment for Q-learning, it still improves results slightly, showing the AI scientists can explore unconventional but interesting algorithm ideas. Now, for example, think of the AI trying to teach the text generator to switch writing styles between Shakespeare to modern English writer. It succeeded, but we are not sure if it discovered a real insight or just made the model bigger. Now, what this table shows now The AI scientists performed well. When going research papers in the large language modeling using four different language models, Claude GPT, DeepSeek, Llama, each model started with 52 total ideas and went through the full cycle, the idea generation and all things, with results scored by the automated reviewer. The Sonnet 3.5 model again came out at the top, producing 20 completed papers with an average of 4.05 and a maximum of 5, meaning several papers uploads the strong level of neuro IPS style. GPT-4o followed, completing 16 papers with a lower mean score of 3.25 but showing good experimentation success. DeepSeek, that was the cheapest one, that's $10 per run and more consistent, completed 23 papers through the average quality of 3.21, remained below the top models, and the Llama, while the easiest to deploy, produced the weakest output, that's 2.31 roughly, that's weak reject quality. Now, focusing on the grokking, a fascinating phenomena on machine learning where a model suddenly starts generalizing well. Long after training loss has already stabilized using the template, the AI scientist explores why and when this happens by training transformer models on single simpler modular arithmetic tasks like learning addition or multiplication. The experimentation followed a power at AL 2022 and aimed to uncover what affects the timing of the sudden generalization. The generated paper shows diverse and creative ideas. Unlocking grokking tested different weights initializations, finding that Xavier and orthogonal initialization made models grok faster than standard ones. Grokking accelerated use layer-wise learning, giving upper layers higher rates for quicker generalizations. Grokking through expression or compression tried linking grokking to minimize description length. Through it analyzes was shallow and even included a hallucinated figure lastly. Accelerated mathematical insights propose a clever data augmentation method like operand reversal and negotiations to speed up learning, showing that simple input variation can strongly affect generalizations. These studies reveal that the AI scientists can replicate real scientific curiosity, pausing hypotheses, testing variations, and even making small mistakes like incomplete related work sections, just as beginner researchers might. Think of grokking like a student who seems stuck for weeks, then suddenly aces the test. The AI scientists studied the classroom tricks like different learning rates or examples, make that make through that happens faster. It makes it faster, like a sudden increase in it. Now, this table summarizes how well the AI scientific performed in generating research papers on grokking analysis, comparing results across what we were doing from the start, comparing the four language models, that's Claude, GPT, DeepSeek, Llama, and all things. Each model began with 51 total ideas, then automatically ran experiments, wrote papers, and had them reviewed. The Sonnet once again delivered the best overall with 25 papers and a mean reviewer score of 3.44 and a maximum score of 5, indicating several papers approached the strong accepted level. GPT-4 followed with a fewer completed papers, that's 13, and a lower mean score, 2.92, showing it was capable but inconsistent. DeepSeek Coder, while the cheapest, surprisingly executed the most experiments, that's 38. Earlier it was 23 and that was also maximum one, and produced many complete papers though with slightly weaker average, that's a quality of 3.13. It's acceptable, okay. It's also cheaper na. Llama 3.1 45p again performed the weakest but low mean and max scores like 2 to 3. Overall, these results highlight a trade-off. More powerful models like Sonnet produces high quality papers, while the smaller or open weight models are cheaper but less reliable. Now, discuss the limitations and ethical concerns surrounding the AI scientists, explaining where the system still struggles and why safety measures are crucial. Although it can generate new research and automated reviewers has weaknesses. Its evaluation data on ICLR 2022 might overlap with pre-training data, and it can yet view figures or interact its like it can also be like a real reviewers. The AI scientist also faces it often. It's a common failure model. Similar ideas fail to implement complex ones, produces errors in LaTeX, or even hallucinate results and citations and all things. Sometimes it misinterprets data or matrices, so human validations remain essential. There are also safety tricks. For instance, the AI once caused uncontrolled systems calls and excessive memory to showing that the need for sandbox and restricted accesses. On the ethical side, full automation could lead to mass paper submissions, overloading reviewers, or spreading low quality research. Worse, if connected to real world labs, robots, or coding systems, it could unintentionally create harmful biological or software outputs. Hence, aligning such systems with human values and maintaining transparency are critical. Let's test an example. If imagine a self-driving driving lab that can design and test chemical compounds. If it's not properly supervised, it might accidentally produce something dangerous. The AI scientist faces a similar risk in the digital world. Now, let's discuss and summarize the key contributions, significance, and future potential of the AI scientist. The author explains that it is the first framework to fully automate scientific discovery, from idea generation to all things experimentation, paper writing, and review, demonstrating that this capability within machine learning research. They emphasizes that teaching the AI to write papers isn't just symbolic, but is essential. It helps humans to interpret the discoveries, standardizes evolution through conference trial reviews, and integrates the AI into the existing scientific ecosystem. Remarkable, the system produces meaningful research papers for only around $15 each, showing the potential of democratize scientific progress. The experiments ran on the NVIDIA one, that was 8 cross NVIDIA H100 node for a week, proving that the high efficiency among models tested, Sonnet 3.5 consistent, achieved the best quality papers through open models like GPT and Llama. They were the cheapest but transparent alternatives. The authors also envision future improvements such as adding vision capabilities for figure, incorporating human feedback, and even enabling the AI scientist to refine its own code, essentially a self-improving research loop. In the long run, they imagine an AI-driven ecosystem where the AI researchers, reviewers, and even conference coexist with humans, amplify creativity rather than replacing it. What I was feared of, they are not replacing, they are coping with it or collaborating with it. So that's all the paper is, and it was what a fun paper to reading it, and it was like fascinating for me to like see an AGR doing all those things from ideation, experimentation, coding, paper review, and all things like a human real. The six score is quite a good, and I really learned a lot from it. I will now do the experimentation over it, like the coding purposes after how to make this one. So see you in the next video. Thank you.